Good afternoon, everyone, and welcome to this live interactive session for the course Advanced Transition Metal Organometallic Chemistry. In this course, mainly we will summarize the weak content. In this session, we will mainly summarize the weak content and we discuss some assignment problems, which is like sample problems, that is different from the portal assignment. By solving this problem, for better understanding the course content and how how the problem in the course, that is in the assignment, how to approach the problem. So the next 5 minutes I will wait for the people, if anybody came. If not, then I will start this discussion from my side. I will wait for next 2 minutes, then I will start discussing the question. So in the last three interact or four interactive session, what we did summarize. We first summarize the weak content, going through the slide, and after that we are solving the question. But from today onwards, I think it is better to directly go to the question and then uh, finding their approach, how to solve it, and with the solving approach, I will discuss the main important week content mm, in this week. So that will be, I think, better for understanding the course and the content of the particular week. So from today onwards, I will not discuss the mm, content through slide by slide, but I will directly go to the question, and by solving the question we will discuss the important content. I will wait for another 2 minutes, then I will start discussing the question. Okay, welcome everyone in week 5 live interactive session for the course Advanced Transition Metal Organometallic Chemistry. So as no participant came yet, so I am continuing this session from my side, and if somebody came, then we will join. I have also discussed the problem which is asked in the discussion forum in the last week, that is the week 4 interactive session, and now I have also posted the answer of this question in the discussion forum. So I request everyone, whoever watching this video later on, to please ask your question on the discussion forum if you have any doubt, if you cannot join this session. So from now I will continue the session from my side. I will discuss some 10 to 11 sample problems which is closely related to the assignment problems, and closely related to this week content, and by solving them I will discuss their approach, how to solve this question, and I will also discuss the theories behind this question. Okay, let's start this today's discussion. So when I am sharing my screen, I will turn off my video. When I will talking, then I will turn on my video again. As the course suggests, advanced transition metal organometallic chemistry. So from the week 1 to week 5, we have seen that we have discussed some different types of ligand system, starting with the 3 carbon system, that is the allyl system, then that is allyl cation, anion, radical, then going to the 4 carbon system, and that is the cyclobutadiene and the normal butadiene, their bonding structure, reactivity, preparation, and their molecular orbitals also. Then we move to the most important cyclopentadienyl system, that is the 5 member system, we have which forms the complexes like metallocene, which is more important in this category. So and they have in for cyclopentadienyl we have discussed their preparation, their molecular orbitals diagram, that is the metallocene molecular orbital diagram, and their reactivity studies, aromatic substitution reaction in cyclopentadienyl ring. And then with the metallocene we transfer to our discussion to the metallocyclopentadienyl hydride, halide, carbonyl and nitrosyl complexes. Also in that complexes we have discussed the nitrosyl ligand system, carbonyl ligand system, their electron count and their reactivity and their electronic properties, binding mode, linear binding, band binding, etc. Now uh, from this week we have moved from our 5 carbon system to the 6 carbon system, that is the arene system. Most important in this thing we need to remember that whatever the ligand we are considering earlier, that is the cyclopentadienyl ligand, mainly act as a anion, that is a negative charge on it. But here for arene system, that is the C6H6, mainly the benzene ring, which act as a neutral ligand. So it is in the reactivity and properties of these bis arene metal complexes is quite different from that of the metallocene system. So now with this discussion I will go to the first question of today's discussion, that is the question number 1. This question says the product of the following reaction is. So these compound, that is complex like iron Cp2CO2, these complex I have already discussed earlier. This complex is very important complex, and from these complex many questions are asked in different exams. Now, to answer this question, the most important thing to know for this complex is know the structure of these complexes. In the last few series I have discussed multiple times the structure of these complexes, and there is one special features for these complexes, that is the fluxional behavior at room temperature. That also can be addressed in previous lectures. So now our question is the product of the following reaction. So what will be the now first I will draw the structure of this complex, because this is the most another important structure in this organometallic series. So structure of this complex is Fe, CO, Cp, CO. This is the important structure, and we need to remember this. And as this molecule is structural, that is that this Cp ring and this Cp ring is trans to each other at room temperature. This is the bridging carbonyl group, this is the bridging carbonyl group, and this is the terminal carbonyl group. At room temperature this bridging carbonyl group and terminal group carbonyl group undergo rapidly exchange, and this Cp is undergo the transition from trans to cis as iron, Cp, CO, CO. By this ring opening, that is the opening of these bridges, this. So this is the cis form. So the structure of these complexes is very important. So now our question is what will happen to this I with the iodine. Iodine is a halogen. and its oxidation state is 0. Here our metal center is also in the 0 oxidation state. No, class 2 oxidation state. So what will happen when it is so as we seen in our lecture that these types of dinuclear metal complexes on presence of halogen, that is I2, will undergo the oxidative cleavage of dinuclear metal precursor by the halogen. So what will happen here, this cleavage of this metal bond will happen, and iodine here will be I minus, that is the reduction happens and the metal center will get oxidized. So our answer for this question will be FeCbP CO2I. So mm, so this is the oxidative, so this is called the oxidative cleavage of binuclear metal precursor by the halogen. So this is a very important question. We need to remember that in metal carbonyl complexes, there is a dinuclear metal carbonyl complexes in presence of halogen, it undergo the oxidative cleavage, that is oxidative cleavage. So here our answer will be FeCpCO2I, not this one. This one not. This here looks like similar, but here is the I2, CpI2. So this will be answer will be FeCpCO2I. So this will be our correct answer. With this discussion, I am going to the next question. So the next few questions is about the or molecular orbital diagram and the bonding interaction of the eta 6 C6H6 that is arene metal complexes. This is the question number second. Question number third is also the with the orbital diagram question from the molecular orbital diagram and interaction of the eta 6 arene bis arene metal complexes. Also the third question is also related, slightly related to that. So for to discuss with these three question, first we need to understand the molecular orbital diagram. So here I will explain the molecular orbital diagram, that how what is the main molecular orbital which is responsible for eta 6 arene molecule to interact with the metal, and what are the metal orbital to interacting with this discussion is also previously done with the cyclopentadienyl system, but here this discussion will also done with the, that is the one carbon mode system, that is the eta 6 arene system. So without wasting any time, I am going to discuss this question with the, so eta 6 arene, eta 6 C6H6. So that's basically an arene system. What it suggests? It suggests that this is the arene system. So here we have the metal here, and then we have the metal. This is the metal we have. This is the eta 6 mode of bonding. This is the eta 6 mode of bonding with the bis arene systems. So now as we have seen for the cyclopentadienyl ring, that is the number of carbon atom will be exactly equal to the number of molecular orbital formed. So here we will discuss the, so here we will first discuss the molecular orbital which is available for bonding for this eta 6 arene. Then I will discuss the then I will discuss the how they are interacting with the metal to form the molecular orbital. So, uh, so the first molecular orbital is, that is this one. That is these here we have no nodes. That is number of node equals to 0. That is this is the lowest energy molecular orbital. Here all of these things will be on the same phase. So here there is no node, so and we are calling this orbital as A1G. So we are calling it orbital at A1G. So depending upon the phase we are calling it A1G. So for the one adenine ring, so so it has the no nodes. So going to the next thing, that is that will have one node. So here it is drawing like this. So here we will have one node. So one node can be from here. This is for the one possibilities. Another possibility is that node which we are discussing, that can be with the atom, that is this one. So here we will found that there is the two possibility for the one node system. So here the distribution, that is the phase of this, will be like this. As you all know that when the node passes, the phase of the orbital changes. So here we are calling these two sets as these two orbital have the number of node equal to 1 and both have the number of node equals to 1. That's why we are calling it a degenerate orbital, and it says that is called as U1G. Okay. Now so 0 node, 1 node. Now we are coming to the number of node equal to 2. Here also we have the two possibilities to have the two nodes. We are calling them E2G. This is the one possibility to have the node along the bond, that is like this. Here if it is like this, then our diagram will be these, 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 and these. This is the number of node equal to 2, and this is the one combination. Another combination is this one and this one. One is through the atom and another is through the bond. This is the another combination. Here we will have this here also we are having that is the two sets of orbital which have the number of nodes equal to 2. So we are calling at E2G for one set. So now for the last, that it is the having the 3 node. So our 1 2 3 4 5 orbital is gone. As I told, that number of carbon atom will be equal to the number of molecular orbital available for bonding. So here we will have 6 molecular orbital which is available for bonding. So for here we will have the 3 node. The possibility of 3 node is 1 2 and 3, and this dotted line represents the nodal plane. So if I draw the lobes of the p orbital will be, and their sign will be like this. So if this is up, this will be down, this will be up, this will be down, this will be up, this will be down. So here number of node equals to 3, number of node equals to 3. So now we are calling it at now we are calling this as B1G, B2G. We are calling it as B2G. So here is the 5 orbital where our A1G is sorry. Then we are draw this orbital according to the energy level. So our A1G is like this, A1G. Then we have two degenerate U1G. Then we have another two degenerate E2G. Then we have non-degenerate B2G. So this is the energy of the orbital which is available for this bis array system for bonding with the metals. So this is the energy available for this, and this is the orbital available for this ligand. So now we need to know which orbital in interacting to the which ligand. So for that we need to take the the two types of thing, which is like one for as our bis array system contain these two ring, so their symmetry will be like if it is A1G, it will be A1U, as their symmetry will be reverse. I can show for a representative example. If this is A1G, this is A1G, so if its symmetry is all are up, then the symmetry of the above ring will be all the phase will be down. That is the only possibility when this can interact with the metal. So this is our interaction for A1G and A1U for the two array system, and the orbital which perform interaction with these is the metal orbital. So metal orbital is S and D z square, dz square. So these two orbital having the that is the gz square. So these two orbital interacting with the metal to form as a, this gives rise to the sigma bonding interaction. Like the same way, these two orbital will form the interaction as the pi interaction with the metal. Also these E2G also form as a pi interaction with the metal. So our U1G, when we are talking about the U1G, U1G, we will have also, that is we are talking about the U1G. Now we will have the another combination of E2G. So for the pi or so for the pi, so now we get to know that for sigma, so A1G and A2G, A1U, these these two orbital A1G and A2U, these two orbital undergo the sigma interaction, with the metal S and D Z square orbital, whereas the pi systems like whereas our pi system like U1G and U1U undergo the pi interaction with the metal with the px, py and dxz and dyz. So this is the pi interaction of the metal. So preferably these U1G is interacting with the dxz and yz, whereas U1U interacting with this px and py orbital. Another interaction which is remaining, that is the E2 E2G and E2U. This is also responsible for the pi interaction with the metal orbital with the metal orbital. Now our so these two orbital are mainly interacting with these metal orbitals. Now we are going to discuss our last orbital system, that is the B1G. No, this is not the so this is not the metal interaction. This is from the delta types of interaction. So our E2G and E2U is from the delta type of interaction delta type of interaction with the dxy and dx square minus y square, whereas these orbital that is the B2G and B1U, these orbital remains non-bonding in molecular orbital, that is it is not interacting any other orbital of the metal. So here you have seen that A1G and A2U is forming the sigma interaction with the S and D Z square orbital, whereas U1G and U1U is giving the pi interaction with the Px, Py and Dxz and Dyz, whereas E2G and E2U undergo the delta type of interaction with the metal dxy and dx square minus y square orbital. So how this is interacting is to show that we have our two system um, like this, I am discussing in more details because next on the three questions is depend on this molecular orbital diagram, and we need to understand the the diagram first. So here for the for this, like E2G, we have the two nodes. So one combination I have already told that through the bond. So if I node is like this, like this, so the bonding will be here like this way. This so as we have done in this side, and the other adding system is just below the metal, so this symmetry will be just reverse. This symmetry will be just reverse of the above one. Okay, so for this we need the delta type of interaction, that is the E2G E2G system. So for this delta type of interaction we have our orbital, and another combination will be sorry another combination will be the node is with these and these. So there the combination is like this and like this. So if we start like this, so then this above one will go to the below side, and the below one will go to the upside, and this up one will below. So now for this interaction we have mm, this orbital will interact with the metal orbital of dxy. Dxy have that this kind of orbital. So here we have seen that these lobes of the will interact, this will interact with these two, and these two will interact with these two lobes. So and for this one it will interact with the dx square minus y square dx square minus y square orbital, which forms as a delta bond. This delta bond also seen in our last array system. Now you want to see the molecular orbital diagram of these. So with these, as no participant is there, so I will am discussing this thing from my side only. Well, so this is our molecular orbital diagram um, for our um, for our bis adding uh, metal complexes. So here we are considering the chromium complexes with the electron filling, that is the D6H, each have the, this is the point group. Point group is the D6H. So here we have the A2U and the A1U, which I already shown that it is a number of nodes equal to 0. It has a 1 node and it has a 2 node and it has a 3 node. So now here this A1G is interacting with this A1G of the s orbital, and this A1G is also a s orbital of the to give the A1G bonding and A1G star this antibonding orbital. Now the A2U has no other with the symmetry in the metal orbital, so this remains as a non-bonding orbital, where the U1G and U1U of these interacting with the U1G of the p orbital and the p orbital and d orbital to give this pi bonding and pi antibonding orbital, whereas then this E2G and E2U is interacting with the E2U of this uh, metal E2G orbital to keep the one of the pi, and another E2U remains as a non-bonding orbital, whereas this E1G from the d orbital remain as a non-bonding because no other interaction is there. Also this here the E2U also remains as a non-bonding in nature, and the energy of the B1G and B1U and B2G is so high that it remains as a non-bonding and without any interaction with the metal orbitals. This is the molecular orbital diagram for the arene system. Here we are considering the 4 orbital for the E set and the 2 orbital for the A1 set and B1 set, because we are considering the 2 ligand that is the 2 arene ligand for the one metal arene complex. That's why we are considering the 2 orbital, as I have already discussed this with the help of I have already discussed this here. This is the one sets of orbital E2G. This is the another sets of E2G orbital. So it is this is for the one arene system. This is for the one arene system, and here if CR is there, then this is for the another arene system. So here we are taking consideration of the 2 orbital from the 2 arene system. The electron filling of this orbital is very interesting, and this is the chromium complexes, where these chromium contribute the total 6 electron, and here the chromium is zero oxidation state, contributing the 6 electron, and this is also so total 18 valence electron found for these chromium complexes chromium bis arene complexes. So this will be 2 2 8 this 4 and 2. This is the total 18 electron filling of these complexes. We will come to this molecular diagram one more time when we discuss the one question with the number of electron or number of antibonding thing, number of bonding electron count for the one of the chromium complexes. Now we want to go to our second question. After this discussion, I think it will be clear to answer the question number 2. Now I am going to the question number 2. So now here it is saying that A1G orbital orbital of eta 6 is interacting with the metal orbital, as we know that this in the drawing A1G orbital have no nodes, that is this one. This is the A1G orbital. So these types of A1G and A2 A1U, these orbital can only interact the metal orbital, that is the d z square and s orbital. So for metal we have the 5d orbital, that is dx square minus y square dxy dyz dxz and dxy. These then 3p orbital px py pz. So with these types of symmetrical interaction where is no node is present, only this z square and s orbital is responsible for this interaction, and the answer will be z square and s, and this gives the sigma type of interaction. This is the sigma type of interaction. Sigma types of interaction is given by this adding these adding metal complexes with eta 6 C6H6 ligand. Now so this question is very easy if you understand the orbital diagram and the orbital picture of the 6 molecular orbital which is available for the eta 6 C6H6 for bonding with the metal. Now I am going to the question number, this is question number 2. So now I am going to the question number 3. So here also the question is which I discussed few minutes earlier. That's the for beta adding metal eta 6 complexes, which orbital is responsible for delta interaction. So we know that E2G orbital is always responsible for the delta interaction. So what will be the structure of the E2G orbital? We can draw that E2G has the number of node equals to 2. So this and here the possibility is also 2, and this E represents the degenerate orbital, whereas A1 B1, that is the alphabet AB, represents the non-degenerate orbital. So here the orbital that is the 2 nodes, and one from the here and one from the here, and here that can be one from the here and one from the here. This is the one from the through this atom which will have nodes. So here the orbital diagram will be this one, this, and for this system it will be like this. So this is the orbital diagram for this is the E2G. So for these sets of orbital, know that this from the delta types of this is responsible for the delta types of interaction with the metal orbital, as I already discussed, is the dx square minus y square dxy, which is responsible for this delta kind of interaction. Now coming to this question number 3, it is the number of unpaired electron in eta 6 C6 H6 whole twice Cr plus. This positive charge is important. Sometimes you can miss this charge and your answer will be wrong. So the as I know that eta 6 C6 H6 whole twice Cr is having the 18 electron complex, because 3 into 6, this is contributing 6 plus 6, and another chromium is also 6. Now this, if we remove the one electron it will remove from the chromium. So the electron will be 17 electron, 17 valence electron. But to answer this question, we need to go to the molecular orbital diagram of this. Molecular orbital diagram which I explained. Huh. So here the one extra electron will be out, that is the going out with this A1G star orbital. So here the only two electrons are there. So if one electron goes out, that will be this A1G1. So without knowing the molecular orbital diagram, this question is very difficult to answer. So it is very important to know and to remember that at least this stage of molecular orbital diagram, that is the electron filling positive in the bis arranged system. So the one electron will remove from the here. So in the, that is, there will be the one unpaired electron. So the number of unpaired electron will be 1. So with this discussion, I came to the end of the discussion of this series with the reaction and structure and bonding with the bis arranged system. Now I will discuss the question on the reactivity and some properties of this arranged system. mm, Properties of this arranged system. Properties of this adding system. Adding system. Then going to the question number 5. So now with the discussion I have already completed 1 hour. So now that is the half of the question. So in fifth question is the in between eta 6 C6 H6 chromium, that is the bis adenine chromium complex, and eta 5 C5 H5 whole twice iron, that is the ferrocene. The bond energy of chromium adenine and the iron um, CP, the cyclopentadienyl, are respectively. So apparently when we are getting these types of question, it may be looked that this question is typically like memorizing question. That is the to remember the bond dissociation energy or bond energy is how to remember this. So here particularly these types of question, there must be some logic. As I in my previous discussion session I already discussed some questions where we have solved the question by eliminating the options. In some general and very general method, we can eliminate the two option, sometimes three option, to get our right answer. If I eliminate the two option, our probability will increase to 50%. So with these question is that types of question, and here I will also try to discuss this question to eliminating the option, how to eliminate the option and how to get the correct one. So for the complex, this is the structure of these two complexes I have already drawn here. So here we know that chromium is in a zero oxidation state, where iron is a 2 oxidation state. This is the very important thing to know about these two different types of complexes, where the CPD contributed the one electron, that is the CPD is negatively charged. CPD, whereas this eta 6 arene system is neutral. So this is the neutral system, and this is the cationic system, and this is the anionic system. So to discuss with these, the dissociation energy, we know that the dissociation energy will be more when there will be ionic types of interactions. So here it is the ionic types of interaction, and that's why this dissociation energy will must be somehow higher than that of the neutral types of interaction. For this case also we have seen that the bond distance is also greater here, whereas it is shorter for the ferrocene. So this is the neutral ligand. Here it is the electron. If also in the zero oxidation state, so to giving the electron from a neutral thing to another neutral thing is there will be repulsion. So their dissociation energy must be lower. That is, the dissociation energy means energy required to dissociate the molecule. That is also same the bond energy. It's the energy required to dissociate any bond. So here it will be greater, it will be lower. So in our option we have seen that option B, it is this one is greater and this is lower. That is absolutely correct. Here the difference is very less. Here also this one is greater and this one is lower. So these two options we can easily eliminate by applying some basic knowledge. Here, as the difference is too small, we can also eliminate this option. So our option will be option A. So option A will be the, here the bond dissociation energy will be less than that of the ferrocene complex. Now, with this, we coming to the question number 6. That is the bis arene metal complexes are sensitive and vulnerable towards the oxidation. Now, to overcome this tendency, what do we need to do? Here are three options. That is the replacement of hydrogen with bulky substituent on aromatic ring, replacement of hydrogen with electron donating group, and replacement of hydrogen with electron withdrawing group. This question is directly from the slide, and this is the discussion, and there is no particular region. It is seen that the which arene complexes, as we already shared earlier question in that, this complex has the bond dissociation energy less. That's why this complex is vulnerable, and the the metal center is also electron rich. That's why it is also susceptible towards the oxidation. And with this is the these arene complexes are sensitive as well as vulnerable towards oxidation. These 2 points is now clear with the previous question discussion. Now the replacing now to overcome this tendency, we have noticed that to overcome this tendency we just need to do something. So here this is the replacement of H with bulky substituent. So as you will learn there are less number of electrons, that is electron rich system, that is the ligand and metal. The increase of bulky substituent will make it more steady on the aromatic ring, that is arene ring, which will create the more repulsion. If we increase the bulky substituent, if we create the more repulsion, then the dissociation energy will be more less, that is the dissociation will be less. Now it was now it was 170. It can be, if we use the bulky substituent, it can be go below that, that is the 100 to 50. Then this compound will be more sensitive and more vulnerable towards the reduction of oxidation. So this option is absolutely incorrect when we are adding the bulky substituent on the ring. So here the right answer will be when we are using the electron withdrawing group. There is no such, I don't know any particular reason for that, but maybe the electron withdrawing group is with helps to remove the electron density from the metal in a metal to ligand pi back bonding fashion to give the stability of the system. That's why the electron withdrawing group is stabilizing the system. So as we have already discussed that here the arene system and the metal both are electron rich, and so if we introduce any electron withdrawing group, it may stabilize the system. So here option only option 3 will be the our correct correct answer. With this I is the another question from the reaction, that is the reactivity of the bis arene chromium complexes. So this is the another question. This question is very simple to answer, but if you know these types of reaction, we have also observed in the mm, cyclopentadienyl system. So here it is seen that the eta 6 C6H6 chromium, where it is reacting as a bipyridine, it is converting this bipyridine 3 chromium and C10H8 system. So this here what is happening? This C10H8 is this one. That is the naphthalene ring is forming over here. So with this ligand here, this is also neutral, and this is also neutral. Here it is also forming as a neutral complexes. So here it will be that ligand exchange reaction. Here it is not oxidation, not aromatic substitution, nor metathesis. So the reaction is the ligand exchange. So the CpH6H6 adenine ring is exchanging with the more strongly bipyridine ring with the chromium. When the ligand which you are adding is more strongly bonding, then these types of substitution reaction is happening, like what is happening over here. With this, I am going to the next question of this today's discussion. That is the question number 8. This question number 8 is very interesting, and we need to know something, some reactivity with this adenine system before discussing this question. So with this, we know that this adenine ring is electron rich in nature, but like the cyclopentadienyl ring, it is not susceptible towards the substitution reaction. Why? Because here the chromium is in a neutral metal and it is in a zero oxidation state, so it is very susceptible to oxidation rather the substitution on the ring. That's why this adenine system, the ring substitution reaction is very difficult. But with presence of this condition, that is the butyl lithium, timeda, and Me2H2, this condition is that is this process is called the lithiation or metallation, or particularly the lithiation, when we are using the N-butyl lithium. So this is the N-butyl lithium. When we are having the N-butyl lithium, we are having the lithiation procedure. This is called the lithiation procedure. But as the substitution reaction on these adenine ring is difficult for these bis adenine chromium or bis adenine any metal complexes, but with this method we can substitution can be done. So with this butyl lithium, what will happen? We know that butyl lithium is the reagent for the lithiation, but that is another role of this one, that is the timeda. Timeda has an important role over here. What role it, this TMEDA is not only perform the monolithiated product but it helps to perform the dilithiated product. The TMEDA stabilizes this dilithiated product. So in the first step, what will happen? It will be like this. This is lithium, this is chromium, this. So this lithiation will happen first step, whereas that is you can generate a nucleophilic center over the aromatic ring. So this is part from the substitution reaction. Now here our Me2S. Now I have MES S Me. So what will happen? This delta negative charge, this is the delta positive charge. So these two will attack to the sulfur, leaving of this group. This is also for the same. It is the delta negative and delta positive. So this is the same and leaving the same. So the excess of Me2S and the 2 equivalent of butyl lithium, we are getting this product. Not and we have also seen these types of reaction earlier, that the dilithiated product in the same single aromatic link or the monolithiated product is happen only we are not using the TMEDA. This is the monolithiated product. But here after the monolithiation we are having the mixture of product. That's why the dilithium. But here this lithiation is also not possible in both the aromatic ring with the dilithiation. So here this will attack and this will so this will liberate LiSme2 LiSme. So this will liberate the LiSme to give this product the aromatic substitution reaction. This question is very much important when we know that the substitution reaction. We know that the substitution reaction for this system is substitution reaction for this system is quite challenging, whereas this method with the n-butyl lithium and this will performing the substitution reaction in both the aromatic ring very easily. So this is the another reactivity condition for this eta 6 arene system. So with this I completed the discussion of the 8 question with their approach and the bond. Mainly with this session I have discussed the bonding and the molecular orbital treatment of eta 6 arene system, which is very important to know, like I discussed the bonding of the cyclopentadiene system. With this I am going to the next question of today's series, that is the preferred mode of bonding for arene towards the metals. This question is also directly from the lecture. I did not modify anything. What will be the preferred mode of bonding for these types of arene? There is the higher annulated arene. We are discussing only the eta 6 arene system, but there are several kinds of arene system like this. We can also have this or this one, and also this one, also this one. So this is called the higher annulated system. So with this higher annulated system, what will be the preferred mode of binding? So here the preferred mode of binding is very important. It is the terminal binding, like the metal anionic aromatic system, with the binding with the middle aromatic ring, or binding with the as a eta 2 fashion of this eta 4 fashion. That is the eta fashion mode bonding, whereas binding is the terminal thing. So here we need to consider to answer this question is that is the highest index of local aromaticity. This thing is very important to know the where the metal will preferably binding over the higher aromatic system. So here if we see that for these types of ligand system, this the highest index aromatic thing is that the highest aromatic thing. Here if we see that this is not binding in the aromatic fashion, it is a terminal mode of binding, so this option cannot be correct. With these, this is somehow eta 6 mode and this is somehow eta 4 mode of bonding, so these two options. mm, so with these types of analytic system, this eta 4 mode of bonding is quite not possible, so we can also cross this option. Now with these two, we need to find the highest index of aromaticity. To find this, there is a simple understanding that this aromatic, this one is aromatic, these two, all the folding and aromatic. But if we consider the aromaticity of the middle ring, this aromaticity is sharing over all the three rings. That's why the index of aromaticity of the middle ring is very less, whereas the this aromaticity of the terminal, any of the terminal ring, is sharing with only one aromatic ring. That's why the index of aromaticity is higher here. So the bonding will be not the with the middle aromatic ring. The bonding with the arene will be always in the higher, that is the terminal side. So here the bonding will not happen here. If we consider this ligand system, this will not bonding. Our bonding will be, this will not participate in bonding. So here the bonding will be preferred for either this aromatic ring or this aromatic ring, not here. The similar situation for here also is that it will be formed for the aromatic ring, not the terminal side, not the middle side. So this is the question how to answer, and this is a very important question for this, where this the higher aromatic ring, what will be the preferred mode of bonding. So for that we need to remember that highest index of local aromaticity. With this, I come to the discuss the 9th question of the today's series. The next question is the oxidation state of chromium in it is eta 6 C6 H6 all twice. So this question I have already discussed multiple time in previously, that like this CP2 Fe CP2Fe, that is the ferrocene. Here the oxidation state of the metal is 2, because Cp ligand is anionic, but for whereas eta 5 Cp ligand is anionic. So here electron count, we can, if we go with the neutral method, so it will be 5 plus 5 plus 8, that is electron count in the neutral method to give the 18 valence electron for Fe2Cp. But for the eta 6 C6 H6 whole twice Cr, the electron count will be in neutral method, this will be here chromium is 6 plus 6 plus 6, here it is also 18 electron, 18 valence electron. um, 18 18 valence electron. But here the eta 6 C6 H6 are formed as a neutral neutral ligand, so the oxidation state of the chromium will be 0. Here this is very important to remember to differentiate the ferrocene with the bis adenine eta 6 complexes. With this I came to the end of this the 10 question session. Now the remaining one question is for the synthesizing part of this bis adenine system. Question number 11 is this is the probably the last question of this discussion series, where we are discussing the synthesis of this ligand. The Fischer-Hafner synthesis is applicable for synthesizing. So this is a very easy question to discuss the synthesis of the complex of this adenine complex. This method is very useful. So, this method is useful for synthesizing the bis adenine metal complex. So this is a very easy question, I think, to answer. But this complex to synthesizing this with this synthesizing with these thing, and there are some certain limitation. So we have seen that for Fischer synthesis, this is the adenine system which is synthesized by Fischer and Hafner in 1955. CrCl3 plus Al plus 6 adenine, AlCl3 plus H2O, and so uh, mm, uh, to of sodium thiosulfate and KOH, it is forming the adenine system. So when we are synthesizing the bis adenine complexes with this method, we need to remember that there are certain limitations, like the adenine should be inert towards the, so that no other functional group is attached to the adenine, which can form the adapt to the aluminum chloride. The adenine should be inert towards the this synthesis, and the alkylated adenine isomerizes by the aluminum trichloride, so that alkylated adenine we cannot use. So there are certain limitations for synthesizing the bis adenine complexes using Fischer-Hafner synthesis. Also, as I mentioning that halogen aniline phenols which have the Cl2 Cl aniline NH or phenol OH, this group, that is the functional group having the lone pairs of electron, is forming the adduct with the LCl3, because it is a bis acid. This is difficult to synthesizing the bis adenine complexes when this functional groups present with this method. So with this I come to the end with the today's question discussion session for the week 5 content. Here I think I have discussed most of the important things for today's series. um, Today's I will wait for another few minutes. I think I should stop sharing. So with this I have come to the end of this today's discussion session. As no participant was there, so I'll wait for a few minutes. So whoever watching this video for the course Advanced Transition Metal Organometallic Chemistry, I think this discussion will help you, to solve your assignment problems and the problems in the main exam, and for you will understand better understanding for the course content. And if you have any further question, further doubt, so please use the discussion forum and post a question there, and I'll try to answer these questions as early as possible. I'll wait for another few minutes, then I will close the session. I thank you everyone for whoever will watch this session. So at the last, I am introducing myself as a TA for this, as a PMRF TA for this course. Myself, Subhajit Kundu, I am hosting this session as a PMRF TA. I am a second year research scholar at IIT Bombay. So whoever watch, so I will request everyone who will watch this series, please use the discussion forum to post your question, doubt, anything which you need your answer. So we'll try to get those question as much as quickly. We will try to resolve these questions. I'll wait for another 2-3 minutes, then I will close this session. Okay, I believe that this session will be helpful for solving your assignment problem as well as for better understanding the course. So with this I am closing this session for the live interactive session of the advanced transition organometallic chemistry. Thank you.